Hello and welcome to activity 3. So for this activity, we're actually going to be skipping lesson 3.1, although I will refer to one problem from it throughout this lesson. So in this activity, we're completely switching gears from what we've worked on so far, and we're going to be learning about some attributes of polynomial functions. So our learning targets for today are going to be to sketch the graphs of cubic functions and even some other ones, and then also this idea of end behavior. We want to identify the end behavior of a polynomial function. So first, a quick review of what we have learned about polynomials already. So you know a polynomial is a function in one variable that can be written in this form. It's written, it looks messy, but it's really not. It's just you have a sub n x to the n. That just means a coefficient, and then it's x to a power, and then another coefficient, and then x to one less power, and so on. So it's kind of a messy form, but if you look at here's a function that's a little bit more recognizable to you. You can see that we have what's called a lead coefficient, 7. And we have the degree of that polynomial would be 5 because it's the highest degree of the polynomial. And so then we have each one of these expressions are terms, and terms are always separated by addition and subtraction signs. So we call this standard form. So when all the like terms have been combined and it's written in descending order, then we say that the polynomial is in standard form. Okay, so we have the 7x to the 5th first, then plus 2x squared, then minus 3, the constant. We're also going to talk in this lesson about zeros of a function. And zeros are basically like the solutions to the function. But we're going to see it graphically today. And a zero is actually going to be where the graph crosses the x-axis. So it will be anywhere that the polynomial f of x equals 0. Okay, and so we'll also relate that to the factors of the polynomial. So remember, zeros, factors, roots, solutions, those are all things we called it back last year when we studied quadratics. So if f of n equals 0, n is 0 of the polynomial if x minus n is a factor of the polynomial. We always switch the sign from the factor to the 0. All right, but what we're really focusing on here are the attributes of the polynomial, and that we can actually predict the attributes by looking at the polynomial. So here are some of the things that we're going to go through. So first of all, the constant of a polynomial is always going to be the y-intercept of the graph. So the constant will be the y-intercept. Next, we want to look at the degree of the polynomial. And the degree of the polynomial is going to tell you the maximum number of x-intercepts, or 0, the graph of a polynomial can have. Now, we do know that sometimes polynomials have no x-intercepts, and that's because the zeros are non-real. That's when we get those i's. Okay, but the degree will tell you the maximum number of x-intercepts the polynomial could potentially have. And it also, that degree is also going to tell us some information about how the graph behaves. We say about the shape of the graph at its ends. We're going to be calling that end behavior. And as said before, the zeros of a function are the x-intercepts of the graph. So we did already say that. Okay, now, when we say attributes, just in case you didn't know, attributes mean a property or a quality or a characteristic of a person or an object. So that's what we mean by attributes. Also, in the math terms over here are some reminders of what we call the polynomial if it has these degrees. So if the polynomial is degree 0, then the polynomial is going to be just a constant. And if the polynomial is degree 1, that's a linear, and that's a straight line, just x to the first. You did a ton with x squared last year, and that was the quadratics. And this year we pick up with cubics and quartics, so x to the 3rd, x to the 4th. Okay, on to page 2. So this is a problem number 1 that says we want to take from the previous lesson. And so since we didn't do the previous lesson, I'm just going to sketch this graph for you so we can talk a little bit about it. So in the previous lesson, you would have gone through and sketched a graph that looked kind of like this. It started up high, then it increased, then it kind of hit the axis, then it went back up, got to sort of like what we call a little relative max, and then back down again. So you haven't had to graph anything like this yet. Okay, the most you've done is quadratics. We've graphed a U or an upside down U. You've done that, but this is something that's a little bit new. So this graph is here because it's good it helps us to explain the idea of relative maximum and relative minimum. So this graph actually continues to infinity in both directions. So there's no absolute maximum of this graph. It goes on forever. There's also no there's also no absolute minimum of this graph because it also extends infinitely in both directions. So when we talk about relative, we mean like a place on the graph that is a low or is a high. That's what we mean by relative max and relative min. So for question 2, it says name any relative maximum. So a relative maximum would be like a high point in the graph. And so we can see a high point in the graph is, right about here. And so that's about 20,000. So we would say the relative max is about 20,000. Okay. Now a relative min is like a low point in the graph. And so our relative min is actually right here at right about 0. And so we would call that the relative min. That's the lowest, it's a low point in the graph. It's not the absolute lowest point of the graph. Okay, now looking at a graph, we can also name some x and y intercepts. And so we can see that there are places where this graph crosses the x-axis. So if I notice that the graph crosses the x-axis at x equals 0, it also crosses over here at x equals 35. Okay, so that's what I would say for my x-intercepts, x equals 0 and x equals 35. And my y-intercept is also at 0. So y equals 0. That's where the graph is crossing the y-axis. So next, they want us to use a graphing calculator to sketch the graph of this cubic function. And so I'm going to do that for you. I'm going to go ahead and switch over to my graphing calculator and we'll plug in this function. We can kind of get a look at it. So if I go to y equals, okay, so on your graphing calculator, it's a little easier, so I did put this in a little bit ahead of time so we could see it. But, you just type it in just as it looks. We have 2x to the third minus 5x squared minus 4x plus 12. Now you're going to get your x from the button that's right next to the green alpha key. So you'll see that right next to the green alpha key is the x button. So if you type it in and then you hit graph, you can see your picture. It's, similar to the one we looked at before, not exactly the same. And you can kind of see where we have some relative maxes, some relative mins. You should see a couple of places where I see an x-intercept. So I'm going to just take and trace a little. I can do this with my pen. You would have to trace using your arrow keys. And I can kind of see my x-intercept looks like it's about negative 1.5, and the one over here looks like it's at about 2. Okay, so when I'm going to put my graph in here, I can kind of see that kind of helps me to do my graph. So about negative 1.5 is an x-intercept, and then I also saw one at about 2. Okay, now a y-intercept would be good to know as well, so I'm going to go back and look at my y-intercept, and that's right about here. So on my graph, I can see that that's also approximately 12. So I'm going to go up and put that there. And then I can see that the relative max is just a little bit higher than that. It's up there. So oops, move that down a little bit, and I can kind of see where that is. So that's, just a little bit higher, maybe about 12.5 or so. So now I think I really have enough information to get kind of a good sketch. So, around 12, I can have my my y-intercept, and then just a little bit higher, you can kind of see where the relative max is. And then we had another relative min at 2, and then it went off to infinity in that direction. So right now we're just graphing with what we call sketches. We're just using some of these main attributes to get a picture. And so now we can talk about some of those main attributes. They'll ask us a few questions. So question 5 says name any relative max values or relative min values. So I see a relative max at about, looks like at about 13. So I would say max, let's do max, approximately 13. And I see a min, a low point at 0. Okay, and again, these are just sketches. Okay, I do see some x-intercepts. I see one that was at about negative 1.5. So x equals negative 1.5. I see another one at x equals 2. That's another place the graph crosses the axis. And I do see a y-intercept at about 12. So y equals 12. So we've got some main points that kind of helps us get the general shape of the graph. And that's the idea on those problems. All right, we're going to skip the check your understanding, and we're going to talk a little bit about end behavior next. So end behavior is pretty important. You're going to get a lot of questions about end behavior. So let's talk about what it is first. So the end behavior of a graph is the appearance of the graph at the extreme right and left ends of the x-axis. That is, you look to see what happens to y as x approaches negative infinity and positive infinity. So if we go back and look at our graph from number 1, to describe that end behavior, we would say, let's go back to that graph in number 1, we would say that as x approaches positive infinity, the graph is approaching negative infinity. And as x is approaching negative infinity, our graph is approaching infinity. Okay, and that's how we would write our end behavior. That's the notation that we would use. Okay, and so they tell us that right here. As x approaches negative infinity, y approaches infinity. And as x approaches infinity, y approaches negative infinity. So now we want to do that ourselves. So let's try that on problem number 4. So that's the one we just sketched ourselves right there. Okay. And so it does look a little different. So I'm going to look at as x approaches infinity, I see y also approaching infinity. So as x approaches infinity, so that's how we say x approaches infinity, y also approaches infinity. But as x approaches negative infinity, y also approaches negative infinity. So it's backwards from the one we saw before. The end behavior changed on that one. And we're going to look at what kind of causes that to happen in each equation. But that's how we would write it, and that's how we would read it. Okay, so now we want to look at question number 13, as there's another one for us. And this one, they didn't give us a picture. It says, examine the end behavior of 3x squared minus 6. So they didn't give us a picture, but if you remember back to when you studied quadratics, remember quadratics were always U's, and they were either facing up or they were facing upside down. And do you remember what caused them to go upside down? It was always the a term's sign. So since 3, which is the a term, if you remember ax squared plus bx plus c, since our 3 is actually positive, this graph is going to look like this. So I just know about the general shape of a quadratic, and therefore I should be able to know its end behavior. So quadratics, their end behavior is going to look a little different than what we just saw with those cubics. So as x goes to infinity, y is going to infinity. And as x goes to negative infinity, so that's the other direction, guess what? Y is still going to positive infinity. Okay, and that's, unique to the U shape. Okay, so it is possible to determine the end behavior of a polynomial's graph simply by looking at the degree of the polynomial. And so one of the things you want to do is familiarize yourself with the different shapes of the graphs. Okay, so I want you to copy these down. Okay, normally I would say, let's graph them all on the graphing calculator and explore, but we just don't have that kind of time right now. So I'm just going to have you put them in. So first we're going to do our quadratic. So when you have y equals x squared, that looks something like a u, like that. And when it's negative x squared, well, then that u is upside down. That we should already know. Now, next we have our cubics. So if the cubic lead coefficient is positive, then our graph is going to increase from left to right. If it's negative coefficient, it's going to decrease from left to right. Okay. Now, when we get to our quartics, they sometimes look just like the quadratics, and sometimes they look more like W's. It just depends on like how detailed, how much there is involved in that equation. So if you have just plain old y equals x to the fourth, well, then that ends up looking very much like a quadratic, and it's positive, so it's going to go up. If it's negative, it'll go upside down. And a fifth degree is going to follow a cubic. It's going to do very much the same thing. Look like that. So you should be able to notice that if it's an even degree polynomial, that your end behavior on left and right are going to do the same thing. But if your polynomial's degree is odd, then your end behavior is going to do different things on the left to the right. So as x approaches infinity, you would get positive, but x approaches negative infinity, you get negative, or the reverse of that. So the ones to kind of keep in mind, if you look at, like C, D, G, and H, they kind of go together. And then you can see that A, B, E, and F, they kind of go together. So it's even powers versus odd powers, basically, and that's what's going to help us get end behavior. Okay, so they do a whole bunch of explaining with that, and I kind of did that myself. So what I would like to actually do now is jump all the way to problem 25, because I talked you through all the answering of these things already. And we're going to talk about them in class too. So now what we're going to do is use a graphing calculator to make a sketch of each of the given functions on the axis below. So this is going to take you a little bit of time, but I'll try to do them along with you so that you can follow along. You can always pause the video if you want to, but I'm going to my graphing calculator, not the one on my iPad, because it's going to be too hard to switch back and forth. So I'm going to go to type in my first one, A, which is x to the third, and then it's plus x squared minus 4x minus 4. Okay, and the best way to get a quick window is to hit zoom and then 6, and then you'll get like a nice window that should show your graph. Okay, so the first graph that I got, it was an x to the third graph, and it kind of looked like this. Kind of went up and then down and then back up again, like that. So an x to the third, we can kind of get used to seeing what that looks like. Now let's do part B, which is x to the fourth. Okay, so now I'm going to do x. Remember, you can use the caret key to raise to the fourth, plus x raised to the third, minus 11x squared, minus 9x, plus 18, and you hit graph. And this one's going to show up kind of like that W that I talked about before. It's sort of a W. So it starts up high, and then it hits the axis, and it comes back up, goes up pretty high, comes back down a little lower this time, so not perfectly symmetrical or anything, but you should see the end behavior is the same on both sides, and it's facing up. Okay, it's facing up. Okay. Now, on C, we actually have a fifth degree. Okay, now the fifth degree, so x to the fifth plus 2x to the fourth minus 5x to the third minus 10x squared plus 4x plus 8. Okay. Now this one, when you graph it, I think it comes out, looks a little funny because we've got all these dips, okay? But it starts kind of low. Starts from negative infinity, hits the axis about here, comes down, comes back up. Eventually there's kind of a y-intercept up there. And then it comes back down and back up again. And so you can see that there's a bunch of change of directions, but ultimately it follows the same pattern as A. They're both odd powers, x to the third, x to the fifth, and they're both positive coefficients. It's positive 1x to the third and positive. So it's going to start low and then it's going to end high. Okay, so now we can probably predict for D without too much trouble because we have x squared, a quadratic. So if you graph your quadratic, you should hopefully know it's going to face up, and it's going to be a u. But just to get a good idea of maybe where it lands on our graph, I see that minus 12. Now remember, your constant's always going to be your y-intercept, right? So I should know, as I'm going in, I should know already that I am going to have a y-intercept down here because of that negative 12. So when I hit graph, I can see my u, and I can see, this just looks like a regular quadratic doing like that. And so you can see the end behavior is the same as what we saw for x to the fourth. We've got positive infinity on both ends, the same thing on both ends. It's up, and we got that positive 1 for the coefficient, for the lead coefficient. All right, so now some things about each one of these graphs that we can look at are in the next few questions. So, it says, they ask us a question about number 25. It says, how many zeros does each function in item 25 have? Okay, well, if we back up, we can see that in part A, our cubic had 1, 2, 3 zeros. Our quartic had 1, 2, 3, 4 zeros. Our quintic should have 5. It looks like we only have 4. 1, 2, 3, 4. But this one actually counts as a double zero, which is something you might have seen when the quadratic just bumped up against the graph. It just means two of the factors are going to be identical to each other. And then in quadratic, we have 2 zeros there and there. Okay, so we can talk about the zeros. And that's the number of times that the graph crosses the x-axis. Those are what we call zeros, or what we call x-intercepts, and so on. So remember, zeros can be rewritten as factors. And so I just want to do that on one of the graphs for us. Zeros can be rewritten as factors. So if I write down all the zeros, let's say I write down the zeros for, let's see which one I wrote, which was kind of neat, I guess. Let's say for part A. Part A looks like my zeros might be approximately -2, 0, and 3. Okay, so let's say the zeros are -2, 0, and +3. Remember, we can turn those back into factors. And so to do that, we just have to reverse the signs. So if the 0 was x minus 2, it came from x plus 2. And if the 0 is just 0, well, then that's just going to come from x. And if the 0 is 3, that came from x minus 3. So we always reverse the sign when we write the zeros. And then we can set equal to 0, you can FOIL it out and distribute and get an equation back again. So that's the idea. And remember, those were just sketches, so these zeros might not be exactly perfect. All right, so question 31 we can do pretty quickly. It says, examine the graph. How many zeros does each function have? So let's go ahead in there and let's count the zeros. I see 1, 2, 3. So I see 3 zeros. And here I see 1. This one is going to count as 2 zeros. So 2, 3, 4, 5. So this one will have 5 zeros. And just that 2 of the zeros end up being the same. And that's because of it just kind of bumping the x-axis and not coming, and then coming right back up again. So that's actually going to be a 5th zero. All right. So that just kind of covers some of the basics of the attributes of a polynomial function. And I will go over in more detail of that in class, but I'm going to let you try the lesson 3-2 practice where you're going to actually sketch a polynomial. So you can use your graphing calculator to do that. So sketch your polynomial right there. And then you can name your x-intercepts, y-intercepts, relative max, relative mins, how many factors, what they are, and so on. So you should be able to work on these questions and also talk about end behavior. And then we'll go over again the rules for end behavior and take some good notes on that in class. So thanks everybody.